All right, Gen Chem. Today we are going to learn a little bit about thermochemistry. We've already talked a bit about these a lot, actually. You're going to see some of these diagrams that we've done before. We're going to review them, and we're going to then add on another thing in relating how things can be endothermic and exothermic, and actually figuring out how these reactions, being endothermic or exothermic, how much energy is either coming or going, being added or being released in these. We're going to start doing some calculations. So you definitely are going to want a calculator. And I'm looking around trying to find my calculator. It's buried. So you're definitely going to want a calculator today. Some scratch paper also might be nice. Okay, so our first thing that we're going to talk about is our enthalpy of a reaction. Now, we've already talked about enthalpy a little bit. Enthalpy is really given to us by the symbol delta H. That is just the change of heat of a reaction. How much heat did we start with compared to how much heat we ended with? So it's the sum of what we ended with, so the products minus the reactants. And that basically just tells us the change of the energy. So we can think of the enthalpy or the heat as either a product or a reactant. If it is a product, it is an exothermic reaction. So if delta H is a product, like it is here in this reaction, how it's written on the product side. Oh my. Let's get this back up here. We can say that this is an exothermic reaction. That means that heat is released. This is going to feel hot or warm. But if delta H is on the other side, if it's on the reactant side over here, it's a reactant. This is an endothermic process. We need to put energy into this reaction. And this reaction is going to feel cool or cold. Okay? And we've all had reactions that we have either felt give off heat that are exothermic, and we've all felt reactions that are cool or feel cold. Okay? So let's go here. If the heat content of the products, if the products is greater than the heat content of the reactants, that means we're going to have a graph kind of like this, where our products are higher than where our reactants started. That means heat is added or absorbed from the surroundings. Let me change my color so we don't. So heat is absorbed from the surroundings. That means delta H, look at this, I had to go up. This is going to be positive. So delta H is positive. It's a positive value. I had to put heat into that system to make those products. That reaction is called endothermic. These are the reactions that feel cold or cool. A good example of that is just think about how your body feels when you hop out of the pool at first. Like you're just hopping out of the pool. That air hits your skin and all of a sudden you feel cold. You feel cold because the air around you is evaporating the water on your skin. And taking that water from liquid to the gas state takes energy. It is an endothermic reaction. So it's taking the heat from your body to make that reaction happen, and you feel cold. That's why swimming feels so awesome on a hot summer day, because it cools you down. Okay, next, if the heat content of the reactants right here is greater than the heat content of the products, notice as I'm going down, my energy is going down. The heat is given off or transferred to the surroundings. It's released to the surroundings. And if heat is released, that's going to feel hot. Okay? Delta H is negative. And the reaction is called exothermic. Okay? Now, you've all sat next to a fire, hopefully at some point, a campfire or a fireplace in your house or some other person's house. When that wood is burned, we take the energy from the wood and we burn that wood and we create carbon dioxide and water, which has a lower energy state. That excess energy as we go from wood to the carbon dioxide in the water is given off in the form of a couple forms of energy. We have light from the fire that we can see, and we actually have heat that we can feel. That's why we use fire to warm ourselves up. Okay, so these reactions are going to feel warm or hot because energy is given off, it is released. Okay, so both of these are measure of delta H. Okay, so delta H here is of a reaction is called the enthalpy. It is the heat or the amount of heat energy in a reaction. Okay, so a couple other examples of enthalpy of some common reactions. How many of you guys have used heat packs to keep your hands warm when you go ski or are outside for a long time in the winter? If you've used the little hand warmer packs or the foot warmer packs, you know that they really just have iron filings in them. And those iron filings react with the oxygen in the air to make rust. And as that makes rust, it's going down to a lower energy level. So it releases energy, and that's why it feels warm. This is like the hot hands. If you ever used hot hands or hand warmers. Okay. I like to stick them in my mittens and my gloves when I go skiing. It helps keep my hands warm, especially on windy days when you're going up the chairlift and that wind just cuts through your jacket and your gloves. It helps keep you warm. Now, on the other side, if you've ever been injured and you've ever had to use one of those cold packs from the first aid kit where you have to like burst that little vessel on the inside and shake it up, that little vessel in the inside that you have to pop or break is full of water. And what they're doing is they have ammonium nitrate, which is a salt, an ionic compound salt. And when they burst that reservoir inside, it releases a bunch of water. And usually that water is dyed blue so that you can see that it's released. And as that salt is dissolved in water, it breaks into the ions. Okay? It disassociates into the ions. And as it disassociates, notice as I disassociate, I have to add energy in there to get those ions to disassociate with one another. So that dissociation energy is absorbed. So it's taking the heat away from your body to cause that reaction to happen. And as it's taking the heat away from your body to cause that reaction, it's going to feel cold. This is why it works very well as a cold pack. So this is how the first aid cold packs work. They just take ammonium nitrate and they have a reservoir of water that you burst, you mix it up, and that dissociation of that ionic compound absorbs heat. Okay, now we have looked at energy diagrams before, and we've talked about them a bit. I want to talk about them a bit more. An exothermic reaction energy diagram is going to look like this. Notice our delta H right here is negative. We go from a high energy on our reactants to a low energy thing on our products. So the amount of heat that we end up with is less. So our delta H here is negative, okay? And we also have our reactants over here, and we can also measure the amount of energy that our reactants have right there from the bottom to where our reactants are. We have our products right here, and we can measure the energy of our products. We can also measure the activation energy. We talked about the activation energy being the energy that it takes to start breaking the bonds of our reactants and start making the bonds of our products. It's kind of that in-between molecule as we're going from reactants to products. That is always measured from where our reactants are to the top of the energy curve. This is our activation energy. Now, if I wanted to read this diagram backwards, though, our activation energy would be from where our products go all the way up. So our activation energy of the reverse reaction would be so much bigger. Okay? And then let's look at our activation or our endothermic reaction. So here in our endothermic reaction, our reactants have less energy than our products. That means our delta H is positive. We have to put energy in there to make those products. Energy goes into that system. Okay? Once again, we can still measure our activation energy. Remember, activation energy is from our reactants to the top of the curve. Okay? We can also measure the energy of our reactants. We can measure the energy of our products, okay? And we can, oops, I need to get another color. We can do the reverse reaction. So if I do the reverse reaction, my activation energy would just be from here to the top. So this would be my activation energy at the reverse. Okay? Remember, at the very top of the energy curve on both of this is going to be the activated complex. And that is the highest energy point of the reaction. And we can measure the energy of that activated complex by doing the top all the way to the bottom of that graph as well. Okay, so there's lots of different things that we can measure on these. We can also have scales on this side so we can actually see how many kilojoules we have going on. Okay, so let's look at this next graph and let's give it some scale, okay, so that we can actually put some kind of quantities to it. So this one has a scale. So let's put some quantitative, which is numbers. Quantitative means that I can actually quantify with actual values, data in the diagram. So what is the potential energy of the reactants? Remember, when I read these, reactants are on the left-hand side unless I'm telling you to do the reverse reaction. So we read these diagrams from left to right. That is our forward reaction. If I read from right to left, this is my reverse reaction. So we normally think of reading from left to right being our forward reaction. So my reactants are going to be right here. So if I look at my reactants, I've got 20 kilojoules. Or actually, it's not kilojoules, it's kilocalories. But usually these are in kilojoules. So the potential energy of my reactants, 20 kilocalories. Okay, the products are going to be the far side, on the right side. So if I look at my products, I look like I'm at about 40 kilocalories. What's the activation energy? Remember, the activation energy is the difference between the top of the curve and where the reactants are. Okay, so I'm going to look at the difference between where the reactants are and that top of the curve, which is right here. That's my activation energy, right here. Okay, so 80 minus 20 gives me 60. So I'm going to have 60 kilocalories. Okay, is this reaction endothermic or exothermic? Okay, so my reactants have less energy than my products. That means I have to put energy in. This is going to be my delta H, and it is positive. So because it's positive, it is an endothermic reaction. Okay, what is that delta H or the enthalpy? Okay, so I go from 40 to 20. So 40 minus 20 is 20 kilocalories. Okay, what about the reverse reaction? The reverse reaction, I would start here. So the reverse, this would be my reactants, and the reverse, this would be my products. And I would start at 40, and I would end at 20. So 20 minus 40, 20 minus 40, because we always start where we end. And so this is our final and our initial. We always start where we end. 20 minus 40 would give me negative 20 kilocalories. So notice these are the opposite of each other. Okay? They are the opposite. Okay, let's put in what a catalyst would be like. Okay, remember catalysts, let's define catalysts. Catalysts are not used up in a reaction. They speed up a reaction by providing an alternate pathway. That's really fancy for reaction mechanism that has a lower activation energy. Okay, so if it has a lower activation energy, that means that more molecules are actually going to be able to have the energy to do it. So I'm going to put in a catalyst pathway. It would have a lower activation energy. Notice our activation energy with a catalyst is a lot lower. So because it's a lot lower, we will have more molecules actually being able to react because we don't have to put nearly as much energy in. Okay? So there's another way that we can actually quantify the heat of a reaction as well. It's called Hess's law. And I'm just going to do a couple of examples for you of Hess's law. Hess's law. It basically means the sum of the reaction or the heat of a reaction can be described by this. So the delta H or the enthalpy of a reaction is all the products, all the delta H of the products minus all the delta H of, and these delta H's are heats of formation of reactants. Oh my gosh, I can't spell today. Do you ever have days where you just can't spell? Okay, so we're going to take the heat of formation of all the products and we're going to take the heats of formation of all the reactants. Now, heats of formation are just way that we can tell you how much energy it takes to make certain compounds. And this is found on tables. And here I have a small table. I will always give you a table of the heats of formation. So let's look at a couple of these. So if I look, for example, CH4, this is methane. And the heat of formation for methane is negative 74.8. Hydrogen chloride right here, that heat of formation is negative 92. You'll notice that on these heats of formation that we have just a bunch of different random compounds and different things. So we call these the heat of formation. Okay, so delta HF, and these are always given. Notice on this table though, there are no pure elements. The pure elements, the heat of formation of pure elements, things that are only like oxygen, just oxygen, or nitrogen, just nitrogen, or iron, is always zero. Because I can't make oxygen, I can't make lead, I can't make iron. It comes to me naturally. So if I just have something that's elemental, the heat of formation of that is always zero. These heats of formation tables are for compounds. Okay? Things that have two or more elements in them. Okay? So let me give you a couple of examples of how we use this table. Okay? I'm going to write the reactions really quick for a couple of reactions, and we're going to use this table. Okay? So let's do the reaction really quick of acid rain. So this is how acid rain is formed in the atmosphere. We have water vapor in the atmosphere, or water in terms of clouds. I'm going to put it in the liquid state here. Okay. And then we have sulfur trioxide that is given off when we burn coal to create our electricity. There's sulfur in coal, and as we burn it, it combines with the oxygen and creates sulfur trioxide. And if I put water and sulfur trioxide up in the atmosphere together, sometimes they'll combine and they will make sulfuric acid. And this is what creates acid rain. So when we do this and try and figure out how much energy is happening in this reaction, we're going to take the heat of our products. So we're going to take the delta H of our products. And our products here are, we have one sulfuric acid. First thing we've got to do is make sure this is balanced. And this is balanced. Okay, so I've got 2 hydrogens on both sides. I've got 4 oxygens on both sides, and I've got 1 sulfur on both sides. So let's look at our products. So I have sulfuric acid, and I want to look up where that is. So sulfuric acid is right here. We have a negative 811.3 kilojoules. So let's put that down. So negative 811.3 kilojoules. And then we need to find the heat of formation of our reactants. And our reactants are water in the liquid state. So let's look up that. So water in the liquid state. Notice we have water in the gas state, but I don't want the gas state. I want the liquid state. So, here we go. Water in the liquid state. Negative 285.8 kilojoules. So negative 285.8 kilojoules for that. And we're going to put parentheses here. And we also have sulfur trioxide. So let's look at sulfur trioxide. So sulfur trioxide right here, negative 395.2 kilojoules. Okay, now I like to add both of these groups so that I have the numbers together. So I have negative 811.3 minus, and then I'm going to add these together. So I have 285, negative 285.8 plus a negative 395.2. That gives me a negative 681.0 kilojoules. Okay, so let's look at this. I have a negative of a negative right here. So if I have a negative of a negative, doesn't that make it a positive? It does. So I'm going to take negative 811 plus 681. Okay, so when I do that, I get a negative 130.3. So the heat of that reaction is negative 130.3. So this is, because it's negative, this is exothermic. So this reaction actually gives off energy, and that's why sulfuric acid is made in the atmosphere, because it gives it a lower energy state. Okay, let's do another example really quick. We're going to use a different color here. So we're going to do ammonia. So I have hydrogen and nitrogen, and we are going to make ammonia. This is the Haber process. This is how we make fertilizer. This is how we make ammonia for fertilizer. The first thing we've got to do is balance this equation. So I notice I have 2's and 3's with my hydrogens. So my least common multiple between 2 and 3 is 6. So 2 times 3 gives me 6 hydrogens, and 3 times 2 gives me 6 hydrogens here. So, and I have a subscript of 2 and then 2 here, so I'm balanced. Okay. Once again, we have to take the heat of formation of our products. Okay, so I've got 2 ammonias. So I'm going to look on my table and find ammonia. Okay, so when I do that, let's change this color so that we don't mix these up. Ammonia is right here. I've got negative 46.2. So I've got 2 of them. So I've got to put that coefficient here because I've got 2 of them. So negative 46.2 kilojoules minus, and then I have 3 hydrogens. Now, when I look at this table, there's no hydrogens. Why not? Do you guys remember that elements have no heats of formation? Heats of formation of pure elements are 0. Hydrogen is a pure element, is not a compound, so it is 0. So my heat of formation for hydrogen is 0. And I have 1 nitrogen, but it also is a pure element. So that heat of formation is also going to be 0. So 3 times 0 is 0, and 1 times 0 is 0. So I basically am subtracting 0. So my problem here is I just need to multiply 2 times negative 46.2, right? So when I do that, I get negative 92.4 kilojoules for my delta H of this reaction. Okay. This also is a reaction that, because this is negative, heat is being given off, so this is exothermic. All right, so this is how we use Hess's law to calculate how much heat is going on in a reaction. We can also do this just by an energy diagram, like the ones up top here, okay? So if you don't have an energy diagram and you just have the balanced chemical equation, you can use the heats of formation tables as well, using Hess's law. So there's 2 different ways of how to calculate the energy change in a reaction. Hope you had a great day. We'll see you later. Thank you. Bye.